All right, let's begin. So, how was that quiz? Okay. All right, so that was the first graded quiz, so no pressure. So the first quiz was like a diagnostic, so it doesn't really count. But that one will actually start counting from now on. And I just want to make sure, so yesterday I sent 2 emails from Jupiter. Did everyone get 2 emails? So one was about how to access the homework system. The other is about the fact that the website is currently up. So the website is now up. You can find the syllabus there. You can find a bunch of things there, including a link to these videos, as well as quiz 1 and the answers are there. And eventually I'll post quiz 2 and the answers there. And just a general thing here is whenever I post like a quiz and the answers or a test and the answers, don't always just go straight for the answers, right? You always want to try to like look at what you did, look at what you got wrong, try to figure it out on your own, and then you look at the answers, okay? So there's no shame in getting help, but you don't want to get help before trying very hard to solve the problem by yourself. And yeah, with that, we are kind of going to move on. So hopefully that quiz didn't go too badly. But every Tuesday, every week, we'll have a quiz. The class will start just like this. And yeah, except on the days where you have tests, which you already know from the syllabus. Okay, so let's actually move on. So what I want to talk about now is something that ordinarily I wouldn't talk about at this point, but your textbook introduces the idea pretty early, so I'm going to talk about it. It's called the average rate of change. Very important idea. I probably would have spoken about it later, but if I give you homework now, it'll probably show up because your textbook does it in late chapter 1, early chapter 2. I'll abbreviate this a lot of times like average rate of change, or ROC, I'll do short for rate of change. Okay, so before we move on, let's just talk about what this guy is. Let's look at some definition. F of x is a function. Hopefully you know what a function is. The average rate of change of f of x on, it has to be on a certain interval. So there's some window in which you're trying to consider the change of f, is a measure of how f of x changes in relation to x on the interval. Probably doesn't tell you anything, so specifically, here's what I mean. So here's our function doing its thing. I think that's your f of x, y. And there's a specific interval I'm thinking about, AB. So that's your function is doing its thing on this interval AB. Now, the average rate of change, what we do, how do we measure this change, is visually what we think about is connecting these 2 points with a line. So, the line is not a part of the function. Let's make it a different color. Connecting this point with a line. Passing through those 2 points. That should be a straight line. Does anyone know what that line is called? It's called a secant line. So you have 2 points of interest on a function, you connect them with a straight line, it's called a secant line. And basically what you measure is the average rate of change the slope of the secant line. So basically, here's your A, that's your x value. If you look over there, that'll be your f of A. Here's your B value, which means the corresponding Y value is f of B. And so how we think about this is basically delta Y over delta X, or where this represents the change in Y. This represents the change in X. So it's just talking about how Y changes in relation to X, right, which is what this is saying. Okay? So the change in Y is just the difference between these two values here. So f of B minus f of A, the top value minus the bottom value. And the change in X is just the difference between these two X values. We'll take the right minus left. So essentially that's like y2 minus y1 over x2 minus x1. Same idea. And you get that equation. So that's what we call the average rate of change. F of B minus f of A over B minus A. And that's just a formula we know now. And sometimes, if I get even lazier, I might abbreviate this with f with a little average at the bottom. Okay? So average rate of change, whenever you hear that phrase, you should think about this formula. And of course, it's interval specific, so it's average rate of change on the interval AB. And basically, you connect A and B, the points where x equals A and x equals B with a straight line. You measure the slope of that line, and that talks about the average rate of change. Now, let me show you another way you can talk about the average rate of change, a change in notation. So we're looking at the same idea. Same function, everything the same. So f of x, these are the points of interest. And connecting them with a straight line. But this time we're going to do the labeling a little differently. The first point I'm going to call it x. And the second point, and this point over here, I'm going to focus on the distance between the first point and the second point, which traditionally is called h. So this location here is f of x plus h. Well, that's the x value. The corresponding y value will be f of x plus h. Corresponding x value here will be f of x. And so if we take that same idea, average rate of change, we would get y2 minus y1 over x2 minus x1. You notice that the x's will cancel, and you'll end up with f of x plus h minus f of x over h. And that guy looks familiar, right? That's the difference quotient. It's actually where it comes from. It's the slope of the secant line. So you can also talk about that as the average rate of change. But usually in any context where I say average rate of change, probably the better way for you to think about it is this way. That's the one that's more straightforward to use. You don't have to care about the distance between the x values. You can actually plug in the actual x values. Right? That's going to be easier in general. So that's what it is. Let's actually look at finding an average rate of change and how we might interpret this idea. So something like this shows up on a test or quiz. Let's do an example. Let's say f of x is x squared plus 1. Find the average rate of change of f of x on, let's say, this interval 1, 4. Okay. So a couple ways I could actually do that. I could also say something like for x is between 1 and 4. But I'm going to tell you the interval, I'm going to tell you the range of the x values that I care about. And then what we're going to do is we're going to interpret what that value is. Interpret this value. Give you some intuitive notion of what that means when we actually do this computation. So we're going to do it. Of course, we're going to realize that your a and your b, these are just the endpoints of your interval. So I tell you the limits on the x, and that's pretty much me telling you what the a and b values are. A is going to be the left endpoint, b is going to be the right endpoint on the x-axis. And so here, I'm going to take my f average. This is going to be f of b minus f of a over b minus a. This is going to be f of 4 minus f of 1 over 4 minus 1. How do I find f of 4? Yeah.
Plug 4 into the equation.
Plug 4 into the formula over here. That's 4 squared plus 1 minus, plug 1 in there, 1 squared plus 1 all over 4 minus 1, which is going to be 3. So that's actually 17 minus 2 all over 3, and that's actually 5. Right? So in this situation, what is the average rate of change of this function on that interval? It's 5. Now, interpret that. What do I mean when I say, oh, the average rate of change is 5? Is the interpretation? Basically, you'd interpret it in this way. For every 1 unit increase in x, or in the input, there is a 5-unit increase in y. That's basically how we want to think about it, on average. On average, every time you move over 1 unit with the x, the y is going to increase by 5 units. And that is called the average rate of change. You have that kind of idea. So what this 5 here means, what's that 5 here? Every time you move over 1, when x increases by 1, y will increase 5 times as fast. And now, it's important for you to know that there is a distinction between the function actually making that change versus the function making that change on average. So the function would look like this. That's your x squared plus 1. And if I look at 1 versus 4, it's here, here. So this is the line here. So this is at 17. This is at 2. Now, the average rate of change, remember, is measuring the blue line, the secant line. So it says, okay, if I move over to 2, the secant line, the point that's going to be on the secant line, it's going to jump by 5. So that's actually a 7. If I move over 1 more to unit 3, it's going to jump by another 5 units. It'll jump to 12. Finally, once I get to 4, it'll jump by 5 more units to 17, right? So now the actual function is doing something different at these locations. But it turns out by how the function is moving, on average, it averages out to between this location and that location, there's an average of 5 jumps on the vertical for every 1 jump on the horizontal. And that idea is called the average rate of change. It's like you're using this straight line to see what happens on average of this function on that interval. Overall, the function increased by 15 units when the inputs increased by 3 units. So it's increasing by 5 units on average. That's the average rate of change. Let's look at a slightly different example to give you another important interpretation here. Let's look at this example. Let's look at this one. Find the average rate of change. Of x on, let's do it on the same interval, 1 to 4. Interpret. So, you're going to do your same thing. F average, F of, let me write out the formula. So, the average rate of change formula is a formula I do expect you to memorize. You should know it. If there's anything you want to memorize, you write it down as often as possible, and eventually you'll remember it. So, I write down the general formula first, then I move on to plugging stuff in. So my B here is 4, my A is 1. In this case, I plug in 4 into here. It's 4 minus 4 squared minus 1, 4 minus 1 squared, all over 4 minus 1. That's 4 minus 16, that's minus 12, minus 4 minus 1, that's minus 3, all over 3. So you notice here, on top I get negative 15 over 3, that's negative 5. So, interpretation here. What does it mean to say the average rate of change is negative 5? Well, it means for every 1 unit increase in x, there is a 5 unit decrease in y on average. Right? So again, here, the 5 units is referring to this. Every time x moves by 1, the y will move by 5. It will move by, it's increasing 5 times as fast. The decrease comes from the fact that you have a negative sign here. Right? That negative sign tells you as x is getting larger, y is getting smaller. They're doing the opposite. And as of course, if you let x get smaller, the y will get larger. That negative sign is just interpreted as they're doing the opposite. If one is increasing, the other one is decreasing. The positive average rate of change tells you that they're both doing the same thing. One will increase, the other will increase. If one decreases, the other will decrease. And at least on that interval, on average. The picture here we know what that graph looks like. It looks like an upside down parabola. Not drawn to scale. I mean, that's what it looks like, but if I want to get the picture a little bit nicer here, we go thinner to that place. So this goes at 4, that's y, that's x. Notice that this would intersect at what point? Yeah? This? How do you find that point? Yeah?
2.
It's at 2. Right? That's why I plug in x equals 2, the y value is 4. Right? Set this equal to 0, solve for x. Difference of squares, that factors into 2 minus x times 2 plus x. So it's 2 and minus 2. The points I care about are 1 and 4. Now, it's not what I wanted here. Let's just stop to let's do it like that. So there is a point touching down here. There's a point it's touching up here. If I connect those with a straight line, this one will go over at 3, this one over minus 15, minus 12. And now you can see, every time I move over 1 unit here, I move down. I move down from this point to get to that point. So overall, moving over 3 units, I'm moving down 5 units for every 3 units the x moves across. So it's talking about the behavior of a function in terms of how fast the y value is changing with respect to the x value on average over some interval. And on average means we're just measuring it by the slope of the line connecting the two endpoints. Any questions on this idea? So that's the average rate of change. It's an important idea, and we will come back to it and talk about it a little more, but I just want to introduce it right now because I think your homework is going to have some problems we have to talk about this. So now with that out of the way, we're going to, like I said, we'll come back to it, but for now it's out of the way. Let's actually get to the point of all this, because this is a calculus class, right? So we should be talking about calculus, and we haven't spoken about calculus yet. So in the remaining time, which isn't much time, I think I'd like to talk about what is calculus? What is it? Why are we here? What is calculus? How many people took calculus before? Oh, a lot of you, okay. What was it about? What were you doing when you were in calculus class? What was the point of that class? What were you studying? Yeah?
I mean, my teacher put it like math without a calculator. And
Math without a calculator.
Yeah.
There was a lot of math without a calculator. Like in my pre-calc class, in algebra class, I don't allow my kids to use calculators. Yeah?
I had a teacher tell me that whenever in doubt in calculus, take the derivative.
Whenever in doubt, that's horrible advice, actually. That's really bad. I don't know what that, yeah, no. But you did mention a word there, derivative. That's actually pretty important. It is the study of derivatives. Any other important idea? Yeah?
limits.
Limits. What else?
Integrals.
Integrals. And their applications. That's what calculus is. Now, those of you who've never taken calculus, you're probably still confused. Okay, so it's what exactly? What's a derivative? What's a limit? What's an integral? So, okay, so calculus really breaks down into 2 branches. Okay? So there is one branch of calculus called differential calculus. Now that's the branch that studies derivatives. And it's not something that you do whenever in doubt. There's a very specific reason why you would use a derivative. The goal of this branch of calculus is to solve the so-called rate problem. Right? So there's a very important type of problem called the rate problem. Now, what that problem basically is in a very general, vague sense, it is to figure out how fast something is changing. This is the rate problem. Okay? So, you use derivatives when you want to figure out how fast something is moving, essentially, right? You have something, how fast is that thing moving? Use a derivative, right? So that's called the rate problem. You want to figure out how fast things are changing, right? So you're all alive long enough to know that life is all about change. Nothing stays the same, everything changes, right? So the law of thermodynamics. Everything gets worse over time. That's pretty much what that law says. It's very pessimistic. There's a probabilistic background there, but whatever. Things change over time. The sun rises, the sun sets. The tide comes in, the tide goes out. You know, plants grow, they die, people grow up, they die, right? Things are always changing, they're always moving. What if we could figure out how fast that change is happening? That gives us a lot of power. That gives us a lot of predictive power, right? Like, I will know how to build around my shoreline and how to deal with my shoreline if I knew how fast is the tide coming in. Is the water level rising in this location over time? Is the sea level getting higher? Like, me knowing that and also knowing how quickly it's happening gives me a lot of predictive power, right? So we want to know how fast something is changing. We use a derivative. We use what's called differential calculus. It's a mathematical way to figure out how fast things are changing in some context, right? The other branch of calculus is called integral calculus. Now, this is the study of integrals, right? And that's not the thing you do when you're not in doubt. This is, it also has a very specific goal. The goal of integral calculus was to solve the area problem, it's called. Okay. This is another class of problems, right? Now, what does that mean? Well, this means we want to figure out how much space something takes up. Right? Now, in the two-dimensional sense, that's just an area. Now, in some situations, it's pretty simple, right? If we're looking at a rectangle or a triangle or a circle, I know exactly how much space that takes up. We know formulas for that thing. But we're talking about what was there some irregular shape, right? Where there is no formula for it, right? You have some random irregular blob. How much space is that taking up, right? If you have some random shape in 3 dimensions, how much volume is that taking up? This is called the area problem. Figure out how much space something occupies, right? And whenever that's what you want to do, then one way to attack that from a mathematical perspective is to compute an integral, as it's called. Now, this is also important. Figuring out how fast something's moving is pretty important, but also figuring out how much space. Let's say you're a farmer with a certain plot of land. You're being charged property taxes based on how much land you own. And so you're like, how do you know how much land I own? It's a very oddly shaped plot of land, right? How do I know you're not overcharging me for property taxes? You're telling me I have more land than I actually have, right? Or how do I notice they sell it if they're undercharging me for property taxes? You want to know how much space do you actually occupy, right? That's integral calculus, and you use an object called the integral to actually figure that out. Now, in Calculus 1, in this class, and in a typical Calc 1 class, most of our time is going to be spent over here, figuring out the weight rate problem, dealing with derivatives, figuring out how to apply that to certain things. So derivatives and the application is going to be 2/3 of the class, 3/5 of the class, something like that. Right? It's more than half our time is going to be spent here, and we're going to do a little bit of this guy at the end. But one important thing that we're also going to do, and it's the reason that we're all here, is that we've known how to solve these problems for a long time. Millennia, in fact. We know that there's documented evidence that Archimedes in 300 BC was doing calculus, but we didn't know the important idea that these two things are actually connected. There's a very intimate link between these two things, which you would never think about it. Speed and area, what does one have to do with the other? These are connected. In fact, we learned specifically how they're connected by something called the fundamental theorem of calculus. And this is a theorem that tells you the solution to the rate problem and the solution to the area problem are in fact the solutions to the same problem. You're attacking the same problem from two different sides. And that we knew something about relatively recently, being 300 years ago, where Isaac Newton, his teacher, Barrow, and another mathematician in Germany, Leibniz, figured out that these two fields of math, while for millennia we were thinking of them as separate things, they're actually the same thing. we can study one by studying the other. It's attacking the same problem from a different angle. And knowing about these two things and how they're connected and using one to play off the other, that is calculus. That's why we're here, right? Because one day someone asked Newton about, can you predict how the planets are moving in the solar system? Where's Mars going to be 9 months from now? And he's like, I don't know how to answer that. Give me a second. He goes home, he invents calculus, and then he comes back and answers the question. It's going to be right here. He tried to figure out how fast the planets are moving in the solar system, and realizes that he had to use a lot of tools that are normally associated over here. And you're like, hey, these things, they're actually connected somehow. And that's calculus, right? Two very important problems. One very elegant answer is why we're all here. And we'll start answering these questions next time. So that's pretty much all the time we have today. So tomorrow, we'll begin our calculus journey. I'll see you then.